sample efficiency and random fluctuation. So Iwaki-san, please.
Okay, thank you for introduction. I will start. My name is Atsushi Iwaki from the University of Tokyo. Thank you very much for giving me a chance of presenting our recent work. Has timer start? Is timer start? Okay. Okay. This is the title of my talk. The thermal pure quantum matrix product state is published in this PRR paper. And the sample efficiency and random fluctuation is now under preparation and will appear in archive soon. This is the content of my talk. I first start from the introduction and then introduce what the random sampling methods are. Our results includes both the analytical calculations and numerical results. Okay, let's start the introduction. Thermal equilibrium states are the finite temperature state. They can be expressed in many different ways. This fact is known as a concept called canonical typicality. It means that although microscopic description of all these states differ, they look the same if we focus on local physical quantities or local density matrix. For example, there's Gibbs state, which is a conventional state of statistical ensembles. A typical state is a single pure state, which represents a thermal equilibrium by itself. There are many other different types of states, which we call thermal mixed quantum states, TMQ states. Although they look different, the macroscopic observables are the same in the TPQ state, the Gibbs state, and in the TMQ states. So what could be the difference? The difference could be how many numbers of states are mixed in order to construct these states. For example, the Gibbs state is known to be an exponentially large number of mixture of states, but the typical state is consisting of only one pure state. The purity will distinguish them. Purity is defined as the trace of rho square, where rho is a density matrix, which is well known in the context of quantum information. Purity is nearly equal to 1 when the state is close to pure state, and purity is nearly equal to 0 when the state constructed as classical mixture of many pure states. By definition, TPQ state has purity 1. On the other hand, the Gibbs state has nearly 0 purity because the Gibbs state is mixture of exponentially large number of eigenstates. Between them, there are numerous TMQ states, which has purity smaller than 1 and larger than 0. Okay. The TPQ state is locally equivalent to the Gibbs states based on canonical typicality. Suppose that we divide the system into A and B, like this figure. In TPQ state, if we trace out the degrees of freedom of B, we obtain a local density matrix rho A, and the entanglement entropy obtained by this local density matrix is equal to thermal entropy of subsystem A, and is proportional to the size of A. Namely, it has a volume law entanglement. Therefore, the thermal entropy of the given state, which comes from the classical mixture of large number of states, is converted to entanglement entropy of the typical state. Now, we want to construct such thermal equilibrium states using the MPS. However, since MPS is known to have the area law entanglement, it cannot reproduce the volume law of the typical state. Therefore, it is quite natural that we need to mix many numbers of MPS to obtain the thermal state. However, we found a nice expression of TMPS that can serve as thermal states, which we call TPQ MPS. In this expression, we attach two auxiliaries at both edges of the system. These two auxiliaries are order 1 degrees of freedom. However, it dramatically modifies the entanglement properties. This figure is the entanglement entropy obtained by cutting out the center of the system. At low temperature, showing this red circle, it increases linearly with the size of subsystem A, subsystem N, until it reaches the whole system size n equal to 64. This means that the typical MPS recovers a volume law entanglement. Let us explain a bit more detail the typical MPS. Typical MPS method is a random sampling starting from random MPS with auxiliaries. This initial random state already has a large entanglement, and after the imaginary time evolution, it generates thermal states using only few numbers of samples. Since the entanglement volume law is recovered at low temperature with only few samples, it can be regarded as TMQ state close to TPQ state. Namely, typical MPS shall have quite high purity. We show here the specific heat of transverse Ising chain for different system size and different bond dimension. Unlike usual finite size methods, the size dependence of the result seems to be very small. We also calculated the variance of energy density as a function of bond dimension chi. Here we find that for the usual MPS without auxiliaries, the variance is large in increasing chi. However, if we attach the auxiliaries, the variance scales very well with square inverse of chi. The typical MPS method is a successful method, requiring only low cost both in time and in memory. But there were a few questions left. One of the motivation of the following part of this talk is to clarify why this typical MPS has such features, small L independence and square inverse high variance. Okay. To summarize the first part, we have give state, TPQ state, in between them, the TMQ state. And the difference between them is measured by purity. The degrees of purity can be differ depending on how many mixtures of states is required and how pure each part of the mixture is. Typical MPS is one of the TMQ states which require only small numbers of samples. Okay. Okay. We now construct a general theory for random sampling methods. In random sampling methods, initially, we prepare a set of random states, psi 0. This set is generated from the random distribution and satisfies Ketbuller proportional to identity operator. We perform imaginary time evolution to psi 0 and construct psi beta at finite temperature, like this figure, which is expected to follow the Boltzmann energy distribution. Finally, we calculate physical quantities by averaging their expectation value. In the simulation, the random average are replaced by sample average. And this procedure is closely related to the efficiency of the method. Okay. Random sampling methods have been developed from 1986. The typical-like method or typicality-based method is family of finite temperature exact diagonalization using Hilbert space. And therefore, we cannot access large system size larger than 30. Recently, random samplings using MPS have been actively studied. I will explain these methods in detail later. Now, we consider how can we qualify random sampling methods. Recently, Goto-san, Kaneko-san, and Danshita-san was proposed a very useful quantity, sample efficiency. In that paper, we generate finite M sample and average them. Then physical quantities are calculated with weighted average, where the weights are decided by the norm of each sampled state. If the weight distributes uniformly, expectation values of each sampled state equally contribute to sample average of physical quantities. So the method becomes efficient. Conversely, if the weight vary over wide ranges, small weight samples do not contribute to the calculation, and the method becomes inefficient. To evaluate the variance of the weight, they introduced Shannon entropy of weight, SM, and defined sample efficiency eta as exponential SM over M. If eta nearly equal to 1, the method is efficient, and if eta nearly equal to 0, the method is inefficient. Okay. Now, this is a sketch of how the random sampling method works. if the quality of initial random samples are not good, the imaginary time evolved psi beta has bad quality and the efficiency becomes small. If we have proper random initial state, the psi beta shall be similar to those picked up from the ensemble sampling. Okay. Now we want to know the physical meaning of sample efficiency, which is exponential Sm over m. Sm is an entropy of the weight distribution. We want to express this eta by other measurable quantity. For this purpose, we perform an analytical calculation. The quantity is named NFPF, normalized fluctuation of partition function, denoted as delta z square. Since the partition function z is given by the average of the norm of sampled state psi beta, NFPF is the variance of norm normalized by the square of norm. NFPF is very important in later discussion. These are the outline of the calculation. The weight Wi is proportional to the norm given as Yi. Sm is also described by Yi. Therefore, using the NFPF, sample efficiency is represented as eta equals to exponential minus half of NFPF. The physical meaning of sample efficiency is explained as in the following. The NFPF means the fluctuation of the norm of sampled state. The larger the NFPF, the more the weights fluctuate. Therefore, the inefficiency of the method increases. For example, in the TPQ method, the NFPF can be calculated using partition function and described as exponential of minus system size n times thermal entropy density. So the sample efficiency is evaluated as almost equal to 1 in the thermodynamic limit. Namely, the efficiency is the best so that we only need to choose one state to describe the thermal equilibrium, and it fits with the definition of the TPQ state. Now, other way around, we can explain the meaning of NFPF. Now, for example, if we think about evaluating the physical quantity O, usual thermal states, the variation of expectation value of the operator O is bounded by the square of the norm of O times the variance of the norm of the chosen thermal state. Then we immediately obtain that the fluctuation of the physical quantities are bounded by the NFPF times square of the norm of O. This means that if NFPF is small, we can obtain a more accurate physical quantity. Now, we demonstrate this theory numerically. Before demonstration, I explain recent random samplings using MPS. In MPS-based methods, imaginary time evolution is performed by TEBD or operating MPO. So the choice of initial random states is essential. Random MPS called RMPS was originally proposed as a train of random unitary matrices by the Italian group in 2010. In original construction, the bond dimension near the edge becomes small. This will deteriorate the randomness of initial state. Instead, we develop a new form of MPS with auxiliaries at both edges. In this construction, we analytically show that random fluctuation of one side of the data is scaled as inverse of chi-square. Similar result was obtained in RMPS with periodic boundary condition very recently. Okay. In actual calculation, for simplicity, we take the element of the MPS to be random variables following complex Gaussian distribution. This setting is useful for later analytical calculation. Next, random phase product state or RPPS was proposed by Itaka-san in 2020. It is equal to RMPS with bond dimension chi equals to 1. Therefore, this random state does not have any entanglement, and this makes RPPS inefficient. Goto-san et al. Modified the RPPS and developed the RPMPS plus T method. Before imaginary time evolution, they performed quasi-time evolution by Trotter Hamiltonian, which is different from the original Hamiltonian. This procedure increases the entanglement of initial random states and efficiency, and improves efficiency. These figures shows for different type of initial random states. Goto-san et al. Showed that the RPPS method has a low efficiency so that they couldn't accurately calculate the physical quantities. RPMPS plus T method has relatively high efficient and is better than purification method in some cases. The typical MPS is considered to also have relatively high accuracy. We will demonstrate RPMPS plus T and TPQ-MPS, where we include RPPS as TPQ-MPS with bond dimension chi equals to 1. This is a demonstration for Heisenberg chain with system size n equals to 64. Efficiency eta is calculated using original definition using the sample rate by Goto-san, showing this equality. For typical MPS, we chose bond dimension chi as 1, 10, 40. Chi equal 1 equals to RPPS by Itaka-san, whose efficiency is low and decrease rapidly toward 0. However, increasing the bond dimension to 10 will recover the efficiency in this green data, which has almost the same efficiency as Goto-san's PMPS plus T method. Since we can increase the chi to 40 easily, the efficiency becomes very close to 1 and exceeds 0.9 even for the lowest temperature available. Okay, NFPF delta Z square is calculated independently by sampling and examining the norm of the imaginary time-evolved samples. The same tendency is observed as sample efficiency. We find that delta Z square is large for chi equals to 1 and for chi equals to 10, TPQ-MPS equals the PMPS plus T. Using two data, we plot data as a function of delta Z square for all different temperature and different methods. We find that they collapse to the same curve. This curve is mostly consistent with analytical result. It equals to exponential minus NFPS over 2, showed in red line. This confirms that our analytical and numerical methods works very well. Next, I explain analytical derivation of the scaling formula of the NFPF in TPQ-MPS. I hope the audience who are specialists of tensor networks are familiar with the Penrose diagram I use in taking the random average by hand. We consider a set of random MPS, which we denote random MPS with auxiliaries, which we denote as psi0. We want to evaluate the variance of psi0. For this purpose, we use the equality that variables Ci generated from the complex Gaussian distribution satisfy these relationships when taking random average. We calculate variance of operator O in terms of our MPS psi0 using the Penrose diagram. The random average is expressed from the largest order of chi to the fluctuation of bodies A and B, which are non-commutable symbol. When we connect A and A or B and B, the chi-square behavior appear from this diagram. For example, these lines in A and A forms two circles, and they become chi-square. On the other hand, we connect A and B and A, only chi appears. For example, these lines in B and A form single circles, and it becomes chi. The A to N term disappears since it is subtracted by the square of expectation value of O. The largest remaining terms include a single domain of B. With a system size n equals 3, the examples of leading terms are AAB, ABB and BBB and etc. There are order n square leading terms which contribute to n in this final result. Now, by substituting the Boltzmann factor as operator O, we obtain the NFPF delta Z square to be n over d chi square. Here, small d is the number of local degrees of freedom. For example, 2 in the transverse eigenchain. Let us finally examine this scaling formula of NFPF numerically. This is the numerical result of transverse eigenchain at t equal 1.0 for typical MPS, where results of different chi and n are plotted together. It shows agreement with the analytical result. Results of other temperature also follow this form. Again, we present the formula that the variance of physical properties is bounded by NFPF, shown in this equality. By combining these two, we solve one question on typical MPS, why the specific heat or other extensive quantities do not depend on n. And these extensive quantities have variances also of order n. And when divided by n, the variance of density of these quantities are independent of n. And this is a reason analytically shown why typical MPS provided the result which is almost size-free. We finally discussed briefly about the purity. The purity of the TMQ state is obtained using NFPF, using the similar analytical calculation we introduced briefly. This is the result of Heisenberg chain, where we see that the purity can be actually calculated, and although it is very small, it can classify different series of TMQ states in perfect consistency with the efficiency we showed earlier. The PMPS plus T has the same purity as typical MPS with chi equals to 10. This is the summary of my talk. Thank you very much for your attention.
Okay, thank you very much for nice talk. So now this talk is open. So is there any question or comment? Okay, Okubo-san, please.
Thank you very much for your nice talk. Can I ask a question about the last statement?
About purity?
No, the variance, a sample, random fluctuation of the physical quantities. So I understood that in the case of bulk physical quantities, a constant chi give us the enough precision for the thermodynamic limit. But how about the local quantity? For example, the local magnetization. If we want to calculate the local magnetization, do we need to increase the order dimension of chi to obtain the good result?
Oh, okay. About local quantity. Okay.
So if I remember correctly, if you have,
I think the answer is no. we are thinking about the local quantity as being free of n. So
Mhm.
this this is only fulfilled for bulk physical quantity, not for local quantity.
Okay. Okay. Can I confirm my understanding? So if we have the usual TPQ state, in that case, yeah, in that case, it is enough to use the one TPQ state to obtain the good result for the local quantity.
Oh, yeah, yes.
Okay.
TPQs, the variation, the variance of physical quantity in TPQ states is evaluated as bounded by operator norm square times exponentially small term. So it is okay in TPQ method, I think.
Okay. Thank you very much.
Thank you. So is there any other question or comment? Okay, Harada-san, please.
I have a question about the entanglement volume law. Is there the limit of entanglement in the TPQ-MPS states? And is it related to the virtual bond dimension in this MPS representation?
Yes. Oh, so yeah. So this entanglement P we sell in this talk. I sell in this talk is whole system including auxiliaries. The entanglement entropy of a whole system including auxiliaries. So the TPQ MPS is pure sum of pure single pure state representing some equilibrium in whole system including auxiliaries.
So in the practical case, so the
yes.
maximum entanglement of these states is proportional to the square of bond dimension on the auxiliary bond or not. So it's not so clear for me. So what is the origin of the entanglement? Usually in the MPS state has a very, the maximum entanglement is proportional to the logarithm of chi. So
okay.
however, in this case, so the origin of a large entanglement.
Origin of entanglement is the existence of auxiliaries. There is an upper bound of entanglement entropy, which is given by 2 log high at the whole system, whole physical system. Again, physical system, not including auxiliaries here. Show graph in here.
I see.
So in usual MPS, usual MPS entanglement curve showed page-like curve. The end takes 0 at the end of here. So TPQ MPS is appropriate for extracting thermodynamic entropy, entanglement entropy extract some dynamic entropy, I think. Okay.
Thank you.
Okay, next question. Chami, please.
Your voice is so small. Sorry.
Is it better?
Okay.
Okay.
I can hear.
Yeah. So I may have some technical questions. So first is that do you always choose the bound dimension on the auxiliary side the same as the bound dimension of MPS?
Oh, yes. Initial, yes, it is.
Okay.
In the first place, yes.
Okay.
I take bond dimension equal pi, O bond.
Okay. And then another question is this method more efficient at low temperature? Maybe you have mentioned it, but I didn't. Is it more efficient at low temperature or high temperature?
Oh, yes. I think this method is efficient in also in low temperature, showed in this graph. For bond dimension chi equals to 40, the efficiency of typical MPS method is very high through all temperature.
I see.
So in principle, can you recover the ground state wave function in your approach?
Ground state approach.
Because you are using just MPS. So can you continuously interpolate the ground state and highest temperature state approach?
I think this typical MPS with auxiliaries form is not appropriate for ground state.
I see.
But low temperature, but typical MPS can calculate low temperature, but it is not appropriate for only ground state calculation because typical MPS has auxiliaries. So in calculation, we need to cut the entanglement with auxiliaries at get ground state. So I think yes. Yeah. Okay.